Okay, our last topics in chapter 8 deal with what's called formal charge, resonance structures, and then we're going to look at some bond lengths and bond strengths and sort of compare that to what we looked at in chapter 5, the energy of breaking and forming bonds in a chemical reaction. Okay, so before we get into formal charge, let's do a quick review of some Lewis structures. So we're going to write out the Lewis structure for the carbonate ion CO3 2 minus. Okay, this is going to be our example that we use for formal charge and for resonance. Okay, so step 1, we need to tally up all of the electrons we have for making bonds or having lone pair, so just all of our valence. So carbon is in group 4A, so we get 4 electrons there. Oxygen is in group 6A, so each 3 of those oxygens will give us 6. And because we have a -2 charge, we do know we get an additional 2 electrons for this structure. So when we tally this up, we are going to use exactly 24 electrons to make this molecule. Okay, so oxygens tend to not bond to other oxygens. It's not something that is preferred for oxygen. So especially if it has an oxidation number that's not 0. So we're going to separate out these oxygens. We're going to put the carbon in the center. So we'll have our carbon, have an oxygen, and an oxygen. Okay, so we do know, hopefully, that single bonds are the most common in nature. So if you go back of any of the structures we've looked at, predominantly we do have single bonds. So we're going to start there. So if we start there, we have 1, 2, 3, 4, 5, 6. Okay, so I'm just going to keep a little tally over here. We have 24 electrons we need to use. So far in bonding, we've used 6, which leaves us 18 to go. Okay, so we have 18 electrons to use as lone pair. Okay, so I'm going to start on the outside and work my way in. You don't have to, that's just sort of how I do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So minus 18, we are now done with electrons. Okay, so now what we need to do is ensure that every single atom has what we call an octet. So since these are p block elements, they're going to fill the s and the p subshells to have that noble gas configuration through bonding. Okay, so we have this one here. That's 2, 4, 6, 8. And we have this one here, 2, 4, 6, 8. This one here, 2, 4, 6, 8. So all good there for the oxygen, but now let's take a look at carbon. Look at carbon, we have 2, 4, 6. So as our count total here, we just have 6. Okay, so that's a problem. So what we need to do is shift some electrons around. So we've already used all of the electrons we're allotted to use. So if ever you're doing this and it kind of seems like you don't have enough to make this work, this means you have a higher order bond. Okay, so we have a star here, not enough to achieve the octet, again, which tells us we're going to have a double bond or a triple bond. So since we're only 2 short, this tells me it has to be a double bond. So what we're going to do is just shift some electrons. So this oxygen here in this circle with the 2, 4, 6, 8, if I move some of these non-bonding into bonding, they're still in that blue circle. It's not going to change our count here, but it will increase what we have here. Okay, so these ones here, I'm going to shift down. I'm going to make this a double bond. Okay, so when that's all said and done, we end up with a Lewis structure that looks like this. Okay, so just shifting those down there. Now if we look, still 2, 4, 6, 8, 2, 4, 6, 8, so we didn't touch those. And now for carbon, 2, 4, 6, 8. Now we've achieved our octet there. And for this oxygen here, 2, 4, 6, and 8. Okay, so this is our Lewis structure for the carbonate ion right here. Okay, so a lot of times, especially when you're doing things in Pearson, because it's an ion, we put a bracket around the whole thing, and we say that it's a -2 charge, the whole entire molecule. So anytime you do this with a polyatomic ion, you're probably going to end up putting brackets around it to indicate the whole entire molecule has a -2 charge. Okay, so this -2 charge, we're going to be actually able to see that when we calculate the formal charge. So let's look at formal charge. So formal charge is if we kind of see how electrons have been shifted around in a chemical bond. So we're going to look at how electrons are shifted around in bonding. Okay, so if your electrons weren't really shifted around at all, your formal charge will be 0. So a 0 formal charge means that your valence electrons have not shifted. Okay, we can have positive. So for example, a +1 formal charge means one of your electrons was essentially, your valence electrons was essentially taken away to form some sort of bonding. So positive formal charge, electrons used for additional bonding. And if you have a negative formal charge, that means you've sort of gained, usually it's more lone pair electrons. Okay, so generally speaking, you've gained more lone pair electrons, or you've formed an additional bond, or formed additional bonding. Okay, or formed an additional bond there. Okay, so let's take a look at what that means. So we're going to use carbonate as our example. So I'm going to put that right here again. I'm draw it a little bit smaller to give me some room to work. So what we're essentially doing here is comparing it to the original atom. So if we look at the sort of atom of these, carbon has 4 valence electrons. Okay, so 1, 2, 3, 4. Oxygen has 1, 2, 3, 4, 5, 6. So what formal charge does, it says, okay, here's your sort of atomic standard count of valence electrons. How has that changed when you went in and made this molecule? Have you not changed at all with the formal charge of 0? Have you shifted your electrons in a way to form bonds that normally, say, based off of your Lewis structure, you wouldn't expect to form? Or have you formed, have you gained electrons as lone pair, or gained them through additional bonding and things like that? Okay, so how we calculate formal charge. Okay, so formal charge equals, so we are comparing it to the atom. So we're going to take the valence electrons. Okay, so that's our sort of our start. We're going to subtract 2 things from that. So the first one, we're going to subtract all non-bonding electrons, and then we're going to subtract 1/2 of the bonding. Okay, so what we're saying is essentially these dots here, those belong to the atom. So those are the non-bonding electrons. In a chemical bond, essentially carbon and oxygen are splitting the electrons contained in here, so you only get half of those in the bond. Okay, so if you do this, subtract this, you should get something like 0, +1, -1, things like that. Okay, so let's do this for the carbonate. So let's do this for our carbonate. Okay, so we have essentially 1, 2, 3 species to look at because whatever we calculate for the formal charge here has to be identical to this because they have the same exact bonding and non-bonding electrons. So we'll start with carbon. So carbon looks like this. Okay, so I'm just going to kind of draw what's around it so I can kind of tally this up. So our formal charge, which I'm going to just call Fc, is going to equal valence electrons. So for carbon, that's 1, 2, 3, 4. Subtract non-bonding electrons. So do I have any lone pair here? I don't. Minus 1/2 of the number of bonding electrons. So I have 2, 4, 6, 8. So 1/2 of all of those bondings electrons belong to carbon. So we get 4 minus 0 minus 4. So carbon has a formal charge of 0. So I'm going to go ahead and we'll do it in red and put a 0 right up here. Okay. Formal charge of carbon turned out to be 0. So we haven't really shifted electrons to create additional bonds or anything like that, or gained electrons through, oxygen. We essentially still have 4 valence electrons when we do the tally. Okay, so next we have this oxygen up here. We'll do that. So again, when I do this, I like to just kind of draw out what I have. Okay, so I don't care what it's bonded to. That's essentially what I have in terms of bonding and non-bonding. So the formal charge equals, so for oxygen, we have 1, 2, 3, 4, 5, 6. 6 subtract 1, 2, 3, 4. Subtract 1/2 times 1, 2, 3, 4. Okay, so we have 6 subtract 4, which gives us 2. Subtract half of 4, which is 2. So we have 6 minus 4 minus 2, which gives us 0. So this oxygen has a formal charge of 0. Okay, so nothing that's super exciting yet. Everything is working out. Electrons haven't been shifted around so far that much. Okay, so last, let's look at that. So we have a single bond, O, 1, 2, 3, 4, 5, 6. Okay, so if you look, this is clearly very different from this. So when we calculate this, this formal charge has to be different from this. Okay, because look, clearly not the same number of electrons surrounding this oxygen as we have here. So we are going to see a difference here. Formal charge equals, so still same thing, 6 subtract, now we have 1, 2, 3, 4, 5, 6. Subtract 1/2, and we just have one bond there times 2. Okay, so we have 6 minus 6, which gives us 0. 0 minus 1 gives us a formal charge here of minus 1. So this oxygen has a formal charge of minus 1. So that's this guy here. And if we look, this is the same as this, the 1 single bond and 2, 4, 6 non-bonding electrons. So this one also has a formal charge of minus 1. Okay, so that's what we have here. So we go back up here and look. We do know that this ion has an overall charge of minus 2. So what happened? What does this mean here? So this means 2 electrons were added in to make this molecule right here. So we do find that one of them is essentially here in this valence shell, and the other one is essentially here in this valence shell. So those 2 extra electrons turned out to be right here, and we do know that because of the formal charges of minus 1 and minus 1. And those do add up to give us our overall ion charge, which that's how it's supposed to work. Okay, so that's an important thing about formal charge. If your atom is neutral, they should all sum together to give you 0. If your atom or your molecule has charge, like we see here, they should sum together to give you the overall charge of the molecule. Okay, so for carbonate, we did see that. They sum together to give us minus 2. And again, it always works that way. Okay, so that's how formal charge works, again, you're just sort of comparing it to what is happening with the atom. So I'm going to put a nice sort of box around this. This is what we use to calculate that formal charge right there. Okay. So again, it's just sort of how electrons have been shifted around to make bonds, or again, if you have one of those polyatomic ions and it's an anion, where did those extra electrons go? So this is kind of showing you where those went. Okay, so next topic is we have resonance structures. So next, resonance structures. Okay, so we're going to go back to carbonate to look at that. So if we draw out our carbonate, okay, so we're going to kind of take a look in just a minute about bond lengths. So it turns out if we were to measure this bond length right here, it should be the same as this one. So we looked at this in chapter 7, where if you kind of consider an atom to be a hard sphere and this one to be a hard sphere, the closest they can get together is the distance. And, you know, depending on the radius of the atom, that sort of will let you know what you have there. So it turns out, and again, we're going to see some kind of a graph on this. Single bonds are the longest. Okay, so kind of think about what you have here. The nucleus of this atom is positive charge, so I'm going to kind of draw it there. The nucleus of this atom is also positive charge, and then you have sort of increased sort of area of electron density. So you have positive, positive, negative, they attract. So it kind of pulls these together to have that, you know, bond length or bond distance. If you have a double bond, this one is shorter. Okay, so again, if we look at this one, you still have that positive charge here, but now you have, so I'm going to draw it a little bit darker, now you have more electron density here, because instead of having 2 electrons in this space, now you have 4. So because you have more negative charge here, you're going to get more attraction between the positive centers of these nuclei and this more negative charge. So it's going to pull those in tighter. It's going to make a shorter bond. Okay, so we don't have a triple bond here, but you could probably guess. The triple bond is the shortest. Because now you've put even more electrons in there to increase that attractive force between the nucleus and the electrons. So we have a shortest with that. And I'm going to show you again a plot that sort of explains this right here. Okay, so why is this important? So we're going to go expectations. So if we look at carbonate, our expectations would be that we should measure 2 carbon-oxygen single bond. Okay, so we could look up a carbon-oxygen single bond and we could compare that. So a carbon-oxygen single bond is about 1.43 angstroms. Okay, so just looking it up in a chart, exactly the way we calculated this, say, in chapter 7. And I also should expect to measure 1 carbon-oxygen double. So that one comes in at 1.23 angstroms. Okay, so that's my expectations. If I put a carbonate atom down on, you know, a molecule microscope essentially, and I look at this, I should be able to measure 2 single bonds and 1 double bond. That's my expectation. Okay, so of course, what's the reality? So we'll call it, what do we actually? Okay, so what do we actually measure? We measure 3 equal bonds of 1.36 angstroms. 3 bonds that are identical that have a length of 1.36 angstroms. Okay, so if we look, it kind of appears to be right in between those, right? So not quite a carbon-oxygen single bond, not quite a carbon-oxygen double bond. It's sort of somewhere in between them. So this led to the whole theory of resonance structures. So what this implies is that electrons are fluid. Okay? Electrons are fluid. So we have, oxygens up here with that 0 formal charge, some with -1 formal charge. So how do you sort of account, or how do you minimize that effect? So it turns out having the 0 formal charge is the most stable. So your arrangement of electrons hasn't dramatically changed. So the way you can kind of mitigate that, oh my gosh, this one has a -1 charge and this one has a -1 charge too, is if you share that burden between all three of them. So instead of this one having to take on that whole -1 charge and this one having to take on its whole -1 charge, we're going to share it between all three of them. So what that means is, again, these electrons are fluid. So we have for sure a single bond between all of them. Okay. And then the extra electron and that double bond is actually now shared between them all. So we oftentimes draw that like this, kind of double bond all the way around, something like that. So the reality of the situation, or actual, is that double bond is shared between them all. Okay, so what this means is each oxygen here, 1, 2, and 3, has its single bond and then a little bit of that double bond. Okay, so if you take that double bond and you share it between 3, they each get 1/3 of it. So the actual bond length here is a 1 and 1/3. This one gets a 1 and 1/3, and this one gets a 1 and 1/3. So if you tally this all up together, it should give you the total bonds in carbonate. So again, we go back up here, we have 1, 2, 3, 4 total bonds. Okay, so what we have here, 2 single and 1 double, which adds up to 4. Okay, so 1, 2, 3, 4 bonds. We go down here, we have 1, 2, 3, add up our thirds. That gives us our 4 bonds. Okay, but they're not localized. That double bond is not localized here, how I've been drawing it. It's shared between here, here, here. And so the way we show that is with what are called resonance structures. So I'm going to take my original. So we have our original structure here that we have drawn this way. And we say, this doesn't have to be this way. Okay, this double bond could be over here. So that's another structure that we have. And now we've moved the double bond over here. So this is a second unique structure. This oxygen now has the double bond. It was here, now it's here. And then we can draw a third unique structure where now we have that double bond on this side. And 3 unique Lewis structures that we could draw with just placing that double bond in different locations. So these are all called resonance structures. We have 1, 2, 3. But the reality of the situation is like I said, this is not a localized bond here. Electrons are fluid, they're moving around, and we're actually getting more like a share of that double bond, a 1 and 1/3. And again, we know this because we have measured it experimentally. So this isn't something like, oh yeah, it's probably this way. We've actually measured that there are 3 equal bonds, which fall right in between what we've measured for a carbon-oxygen single bond and a carbon-oxygen double bond, where those electrons aren't fluid and those electrons are localized. Okay, so we do know these bond lengths, and what we measure here is somewhere right in between, again, suggesting that it's an equal length of a 1 and 1/3. So anytime you have resonance structures, the situation is more like this. Okay, so this is the sort of actuality of it, but we represent it using 1, 2, 3 unique structures, 1, 2, and 3, but in actuality, we have more something like this. Okay, so those are resonance structures there. Okay, so I'm not sure if I covered it in the previous video, but let's take a look at common exceptions. So we've talked about the octet here when we made our Lewis structures. So some exceptions you might run into. Okay, so common exceptions. The first one, odd number of electrons. So this is common with nitrogen. He's primarily the culprit there. So some atoms are stable-ish with an odd number of electrons. So instead of having an octet, maybe you're looking at a septet, so like 7. And that's common with nitrogen. You do see that. Okay, so we have less than an octet. Okay, so we've definitely seen that with hydrogen. Hydrogen's too small for an octet. It just has a duet. So hydrogen will have just 2 electrons. Boron is another one. So boron is perfectly fine with 6 electrons. And then we have beryllium, which is perfectly fine with 4 electrons. So less than an octet, some of our exceptions there, these guys here. And we saw this one in the video, more than an octet. So some of our larger atoms like sulfur, phosphorus, iodine, and bromine can have more than 8. So a lot of times they're perfectly happy with 8, but in a lot of times we also see them having expanded octets, so having 10 or 12 valence electrons in their outer shell. And they can accommodate more because they are so much larger atoms. These are in the 3rd row and beyond in the periodic table. Larger atoms, more space around them to accommodate more electrons. Okay. So I do want, with these exceptions in mind, to take a look at sulfate. So we're going to look at SO4 2-, and we're going to draw 2 structures here. We're going to, 1, draw an octet structure. And 2, we're going to draw a structure with a minimized formal charge. So it turns out that even if you can draw an octet structure, a lot of times that's not the actual Lewis structure of your molecule. And we're going to see that with sulfate. We can draw an octet structure, that's perfectly fine, but the actual real structure of sulfate is a little bit different because we can minimize formal charge. Okay, so sulfate, let's kind of walk through it. So we have SO4 and we have 2-. Okay, so let's add it up. So number 1, sulfur gives us 6, oxygen gives us 6, and then we get 2 extra for the -2 charge. Okay, so we end up with essentially 5 times 6, which gives us 30, plus 2 gives us 32 electrons. Okay, so the first one suggests we can draw an octet structure here. So we're going to put our sulfur here, single bond to oxygens. Okay, so when we do that, we have 1, 2, 3, 4, 5, 6, 7, 8. So we already have 8 electrons on sulfur, so we're pretty good there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so there is our octet structure. So 8, 8, 8, 8, 8. And that's what it means to be an octet structure. Every single atom has essentially satisfied the octet rule. So we've used all 32 electrons, 8 times 4 here. Everyone has an octet. Good to go. Okay, so this suggests that we should be able to draw a different structure with a minimized formal charge. Okay, so we've done this oxygen before, but we can run through it again really quick. So this one was oxygen with the single bond So this one we know is 6 minus 1/2 of 2, which gave us -1. So every single oxygen on this structure here has a -1 formal charge. So -1, -1, -1, -1. So we can deduce then that the sulfur is going to end up being +2 if all of this has to add up to give us a -2, but we'll verify that. So sulfur looks like this. So sulfur is also 6. There are no lone pairs, so -0, -1/2 of 2, 4, 6, 8. So we get 6 minus 4 gives us +2. Okay, so no atom on here has a formal charge of 0. So this one is +2, and these are all -1. And so that's, generally speaking, not a very good sign for a Lewis structure where you have nothing in terms of having a 0 formal charge. So this is probably not really how this exists. So we do know electrons are fluid, and we do know that sulfur is perfectly fine with accommodating a little bit more. Okay, so what we're going to do is start shifting electrons around. So step 1, I'm going to say, you know what? I'm going to take these electrons and shift them down. Okay, so now I'm going to have S, double bond O, single bond, and single bond. Okay, so I've just changed one thing. So I do know that this still is -1, this is still -1, this is still -1. Okay, I've done this oxygen before, but like again, we'll run through it real quick. So this is now 6 minus 4 minus 1/2 of 1, 2, 3, 4. So this formal charge is 0. Okay, so shifting electrons around that way, we've minimized the formal charge on that oxygen. We've taken it from -1 to 0. And again, 0 is kind of where we want to be. Sulfur now has changed. Now it has a double bond and 3 singles. So 6 minus 0 is still the same. 1/2 times now 2, 4, 6, 8, 10. So we have 5 here, so we have 6 minus 5, which gives us +1. So by shifting those electrons around, we have taken that from +2 to +1. So we're making some good, strong headway here. Okay, so great. Again, sulfur doesn't mind. Let's do it one more time. Okay, so now what happens? I don't know, choose your favorite oxygen. Let's do it one more time. So what are we going to get there? Okay, so then we have sulfur, double bond. I chose to do it down here, but it doesn't really matter which oxygen you choose for that. Okay, so now we have this. Okay, let's put on there things that we've already calculated that we know. We know this situation gives us 0. So now we have 1, 2 with 0. We know this situation here is -1, so we have that. So really, we're up to sulfur now. That's the only thing that we haven't calculated. So this sulfur has 2 double bonds and 2 single bonds. So still 6 minus 0 minus 1/2 now times 2, 4, 6, 8, 10, 12. So now we have 0. Okay, so in shifting things around, we have a 0 formal charge on our sulfurs. Now we have 3 atoms with 0 formal charge, and we have 2 that only have or carrying formal charge of -1. Okay, so would it be any benefit to shift more around? So we could essentially have sulfur and oxygen swap places. If we took electrons and moved them here, we wouldn't want to do that. So if we took electrons here and made another double bond, then we'd have 0, 0, 0, -1, -1. So what's the difference? Why have the -1 here or here? If you look at oxygen, it is more electronegative. So because it's one of the more electronegative elements, it doesn't really mind having extra electrons. So it is going to be the carrier of the formal charge, much more so than sulfur. So more electronegative elements tend to not mind carrying that formal charge. And oxygen is a really fantastic example of that. Oxygen does quite well containing formal charge here. Okay, so would we expect to have resonance structures here? The answer is absolutely. So I chose the double bonds here and here. I could have easily had them here and here, here and here, here and here, like all the different permutations of that. So we do have resonance structure. So one thing we can look at is what would we expect the bond order to be? So when we say bond order, we mean like single bond, double bond, triple bond, or like we saw with carbonate, we had a 1 1/3. Okay, so we would expect sulfur to do the same thing, take those share and sort of divide it. Okay, so we do know that for sure there's a single bond, and then we do know, like I drew before, that those two double bonds are essentially being shared. Okay, so if we kind of do it out, we have 4 of those, so 1 1 1 1. Okay, so now we have 2 double bonds. So these are the ones that I've broken up floating around. 2 double bonds that we're dividing amongst 4 oxygens. So 2 double bonds that we're dividing amongst 4 oxygens gives us a 1/2. So each of these is a 1 1/2. Okay, so if I add this up, I should get total in this molecule. I have 1, 2, 3, 4, 5, 6 total bonds. So 1, 2, 3, 4, excuse me, 5, and 6. So add that together, we come up with this is 6 total bonds, which again, we know from up here, 1, 2, 3, 4, 5, and 6. Okay, so those 2 double bonds shared between all 4 of these to give us a 1 1/2 bond order. So what is the bond order here? 1 1/2. So if we were going to say predict what this bond length would be, we would look up a sulfur oxygen single bond, we would look up a sulfur oxygen double bond, and we would go somewhere right in the middle. And we would expect it to be somewhere right in the middle of a sulfur oxygen single bond and double bond to give us that 1 1/2 bond order. Okay, so this is essentially it for this chapter. There's one thing additionally I would like to look at, and that is looking at bond length and bond strength. Okay, so I looked up 2 elements. I looked up carbon and nitrogen because carbon and nitrogen are 2 elements that form all 3 types of bonds. We'll encounter carbon single, double, and triple bonds in nature, and nitrogen as well. Tons of single, double, and triple bonds as well for those. Okay, so I looked up the bond length. So a carbon-carbon single bond, 1.54 angstroms, double 1.34 angstroms, and triple 1.20 angstroms. Okay, so that's our bond length. So as you see, just like we kind of talked about for the carbon-oxygen double and single bond, as the bond order increases, the length decreases. So they're kind of inversely proportional there. Okay, so we can say for bond length, as the bond order increases, the bond length decreases. And we did kind of talk about why that was. That was because you have more electrons in between those 2 positive centers that are pulling those nuclei in closer together. 6 electrons in that small area are going to have a much more attractive force to pull those nuclei closer together. Okay, so that's true for carbon. Is it true for nitrogen? And we see the same trend here. Single bond 1.47, double bond 1.24, triple bond 1.10. So it also holds true for nitrogen and any other element we looked up. We could look up doubles, single, double, and triple, we would see the same trend. So bond order increases, the bond length decreases. Okay, so what about bond energy? So we've kind of been looking, we started looking at this in chapter 5. We're going to relook at it here. Now that we can draw Lewis structures out, we can go back and look at sort of energy involved in bond breaking and bond forming. Okay, so a carbon-carbon single bond is 347, double bond 614, and a triple bond 839 kilojoules per mole. So do we see the same trends with bond energy as we saw with bond length? And the answer is no, we see the exact opposite. So for this, as bond order increases, we see the opposite. We see the bond, we'll call it strength, increases. So it takes more energy to break the bond as the bond order increases. So we don't have like 1.5 bonds and 1 1/3 bonds here, but the same would be true there. We did see the length falling for like our carbon, oxygen 1 1/3 bond. It fell right in between the single and double. So we'd expect the energy to fall there as well. Okay, so here kind of putting that together, bond energy versus bond length. So as the bond gets shorter, the energy required to break that bond is a lot higher. And we do know because it's essentially like 3 bonds that are there, so it does make sense that it's, almost triple the amount to break that bond, but also they're feeling a much sort of more attractive force because you do have essentially, you have increased the positive, negative attractive force in that sort of small area. It's going to then take more energy to break that bond. Because again, remember for energy, for this type of energy, energy is proportional to Q1, Q2 over D. So your nuclei are essentially the same, but if you're increasing the amount of electrons in that small space, again, going from, say, a single bond to a triple bond, you're increasing Q2, which sort of follows that your energy should also increase. Okay, so this kind of explains what we see there, and also the fact that we are breaking essentially 1, 2, 3 different bonds. When we get to a triple bond, we have, 6 electrons holding that bond together, as opposed to 2 that we get up here for a single bond. Okay, so that concludes chapter 8. So go back and revisit bond breaking and bond forming that we did look at in chapter 5. But now sort of added into the mix is you should be able to then, if you're given a reaction in standard equation form, you should be able to then draw out the Lewis structure for each of those atoms or each of those molecules. So you should be able to take a reaction, draw the Lewis structure for each compound or molecule in that reaction, and you should be able to calculate bond breaking and bond forming, added in with the fact that now you can take a formula of a compound or a molecule and come up with the Lewis structure for it.